Hello everyone, and welcome back to another Inch 130 video tutorial. In this tutorial, we're going to start covering support reactions, which is kind of the goal for the whole week, is just to determine support reactions. And as you guys will see, it's not that difficult. Most of the videos will probably be pretty short. Determining support reactions, for you guys, of course, is rather simple because they have to be determinate, which means that you have to be able to solve them using your equilibrium equations. And you guys know that for a 2D case, the maximum amount of equilibrium equations you guys will have is 3. So the max amount of support conditions we can solve for is 3, so it won't be too bad. What we'll do this week is we're just going to cover all the different cases. So we got simple beam, which is a pin and a roller. We'll do a fixed beam where one of the ends is fixed. We'll do some cases where the beam's at an angle, stuff like that. So again, the videos won't be too long. And then you're going to think, okay, well, these actually seem really, really simple. And the good news is it is really simple. The bad news is it's simple for a specific reason. So in your final exam, you won't be given a question that's solely just solve these support reactions. It's really easy. So you won't be tested on that. And you're going to go, okay, well, why are we learning it? And that has to do with the following weeks. And weeks being very, very plural. So after we do this is kind of the introduction. We go into other things called trusses, so that's next week. We got 2 weeks of beams following that, and so on and so on. And to solve all those questions, you're going to first need to do support reactions. And support reactions will be a very, very, very tiny little part of solving that entire question. So it's very, very important that we get really good at it now, because we're going to need it for the remainder of the questions, for the remainder of the weeks. Again, it'll become extremely important that we know how to do these support reactions nice and fast, nice and quick, but more specifically, correctly. Because it's one of those things that if you don't know how to do a support reaction on, let's say, a beam question, everything else you do will be wrong. So it's very, very imperative that we get these right kind of the first time. So that's why we're going to cover all the cases. But again, don't be surprised if you think, okay, well, this is actually really easy, because it should be easy. It's not too hard. But again, this is kind of a warm up for future topics. So I think with that said, let's jump in and look at the first example, which is a simply supported beam. Alrighty, so looking at this example, it's short and sweet. It says to determine the reactions at the supports. So very short, very sweet. And if we look at the beam, we have a roller at A, we have a pin at B. All the question would like us to do is to determine the support reactions those provide for the beam under this loading. So before we begin, I think it's best, since this is the first video, maybe just take a step back and we can start deciding, okay, what support reactions will I see in this course? Which ones should I be prepared for? And luckily for you, all I've ever seen in this course is 3 support reactions, 3. So if you guys can get these 3 support reactions, you guys will be good for the rest of the course. That being said, there are other types of support reactions, just very, very rare, because it's very, very hard to come by these in reality. So let's just go over the first 3. So, or the only 3 that you guys need to know. So the first one is going to be a roller. So this is usually symbolized in one of 2 ways. One, just as a circle. So in this question, we see it just as a circle. Nice and easy. Or the second way is we have a triangle similar to a pin, but under it, it has the wheels. So the key is to kind of look for the wheels, or a circle. And the roller is one of the nicest ones you guys can find, because it only offers one reaction, which is going to be perpendicular to the surface on which it rests. So for these 2 rollers, since the surface is horizontal, it's going to provide one reaction force just going upwards. Now, with that being said, remember that this reaction force always has to be perpendicular to the surface. So if I have a roller that's on a surface like this, so something like this, the support it's going to receive will be perpendicular, so it's actually going to be at an angle like this. And I have a video for that later. Don't worry about it. We're going to cover that, because although it's a very rare case to see, it's definitely one professors like to kind of test you with. So that's a good one to know. So again, one support reaction, really nice, really, really easy. And so the second type is one that's very, very common. It's called a pin, or a pinned connection. And how we symbolize that? Well, it's simple. It's just going to be a triangle. And the key is there's going to be no wheels underneath this triangle. So a pin is very specific because it offers the same horizontal, I guess vertical support, or that's not the best term, because as we know we can flip the surface, but it offers support in both the vertical as well as the horizontal direction. So if you guys see a pin, we have to put two support reactions, one vertical, one horizontal. And one thing we're going to discuss too before we get into this is I have this pin here, and I always draw my support reactions as positive, in the positive direction. And you go, okay, Clayton, how do you know it's positive? Or how do you know it's negative? And I don't. So when you're doing these supports, you just guess. And for my guess, I always like to do the positive way. I can throw it into my equilibrium equations nice and easy. And what will happen is if I get a negative answer, that's completely fine, because the magnitude of that answer will be fine. It just means I assumed the wrong direction. And it's okay to assume the wrong direction. As you guys will see, we'll happen to run into that case quite a bit. So it's completely fine. So the last one is called fixed. And this one's a very special case. And that's when you see, I'm going to have to kind of draw the beam for this one to show you. So if you have your beam, what will happen is at one end of the beam or at the bottom of the beam, it'll go right into the ground. So there won't be a circle, there won't be a triangle, it's just going to go right into the ground. And this case is very special because, as you guys can probably guess, it restricts any movement just like a pin. So there's going to be those two reactions right here, so just like a pin. But then since it's so embedded into that wall, it also restricts rotation. And how do you restrict rotation? Well, there would be a support moment. So it's going to have a moment like this. So it's going to have three reactions: the moment and the two translational forces. Now, if we look up here, out of all our combinations, we remember that we can only solve the number of equilibrium equations we have. So if we have three equilibrium equations, so sum of the forces in x, sum of the forces in y, and sum of the moments equals 0, if we look at these combinations, we realize, oh, there's only a certain amount we can do. For example, we can solve 3. So if I had a roller and a pin, that'd be 3 unknowns, we can solve that. If I had just one fixed end, 3 unknowns, I can solve that. But if you're given a question with a fixed end and a roller, you won't be able to solve that because we'll have 4 unknowns, only 3 equations. Now, there were certain scenarios where you actually could be able to solve that, but I believe it was removed this year. Lucky for you guys, because there's a way to determine if there's something called a hinge in the beam, but I don't think we cover hinges, so I'm not going to stress you guys over hinges. But you guys will learn later that, of course, even hinges aren't really realistic. They can be. But what happens in an actual building is there's going to be lots of support reactions, lots, millions even. And for that case, we're going to have to rely on other methods, because the statics that you guys learn, it's only for these determinate structures. But as you guys may have guessed, in structural engineering, we want indeterminate structures. So we want that extra support in case, let's say, one of the columns of a building decides to crack and break. There will be that extra redundancy to help keep the structure up. And there's very specific ways to solve for those, but the methods get quite advanced, so I'm not gonna get into them. So this is all you really need to know for this week, these 3 cases, because what we're going to do for each one of these cases that we go for is we're going to draw a free body diagram, and we're going to replace the reactions. So at B, I have a pin, at A, I have a roller, and I'm just going to replace those reactions with the reaction forces. And then it just becomes an equilibrium problem where we have unknowns in the free body diagram, and we can use our equilibrium equations to solve for those unknowns. So to start this question off, and to start every question off from here until basically your final, so this is kind of a hint, we need free body diagrams. Free body diagrams were kind of optional in the first half of the course. Well, not really optional, because for particle equilibrium you should have done them. Hopefully you guys did them. But for this half of the course, you guys are going to really want to know your free body diagrams, because it's going to be very important for every question that you guys see from here till the final. So I drew my beam here. That's AB. So what I'm going to do is let's start with the support reaction. So if we look at A, we have a roller. So the force is going to be perpendicular to that surface, which we know is 90 degrees. So at A, we're going to have a vertical force like this. And how do I label it? Well, what I usually do is I just take the letter that it's at, so it's A, and then I put a little subscript in which direction it is. So for this one, I'd put A, and I know it's a vertical force, so I'm going to go Y, AY. I'm going to look up at B. I have a pin. So if I look at my little chart, a pin has two support reactions. So what I'm going to do is I'm going to add those in. So I'm going to have my vertical reaction, and I'm also going to have a horizontal reaction. If I can try and draw these horizontal and vertical. And what I'm going to do is I'm going to put B, this one's in the X direction, and the other one I'm going to put B, this one's in the Y direction. So far so good. However, we're not done yet. If we look, we have a nice big distributed load acting over this beam. So what I'm going to do, and this is what we learned last week in force reduction, is I want to try and split that distributed load into a triangle and a square or a rectangle. Those two shapes. I don't want any sort of composite shape, because then if they're a triangle or if they're a rectangle, it's very easy to determine. So if I look, it's very easy to say, okay, well, if I just look at this section right here, I have a nice rectangle. So this is going to be kind of my first one. It's a nice rectangle. And the second one, I see that if I just leave it by itself, I already have a nice triangle. So that's what I'm going to shoot for. So my free body diagrams, what I like to do is just draw the silhouette. So the first one I'm going to draw is that big rectangle. So I'm just going to go up, dot, 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 dot. And I'm going to go all the way across. So it's going to get really annoying hearing me say dot. So I don't think I'll do that this time, but maybe just one dot. And we want to go all the way across. So this is the silhouette of that rectangular distributed load. So I'm going to come down real quick. And what I like to do is where the force acts is I'm just going to put a big kind of force going down. So it's going to act something like this. And what I'm going to do is I'm just going to label it F1. And in our calculations below, we'll figure out what exactly F1 is. So we also see that there's a second one, which we remember was a triangle. So I'm going to just draw that silhouette in. Dot, dot, dot. Oops. I'm going to get up into the fixed support. So let's back off just a little bit, or else this drawing is going to get quite messy. Let's go from this side down. So let's say that we go dot, dot. Something like this. Maybe still, definitely not the scale or anything like that, but that's fine. It's pretty clear, and that's what we go for. So we're going to draw another big force. We'll say that this one is F2. And then the next thing that you guys should do, of course, is we're going to want to label dimensions as well as any parameters that we know. So if we look up here, if we look at the magnitude of the distributed loads, they're given as 900 and 600. So it's best to come down here and say, okay, well, this one's going to be 600. Now, is it newtons per meters? Yes, it is. So best to include units too. Newtons per meters. The one up here is 900 newtons per meter. So now we got those dimensions. We should also include the dimensions of the beam. So we know that the beam is kind of segmented into two parts. So we look up here, it's 3 meters and 3 meters. So what I'm going to do is I'm just going to put 3 meters, 3 meters. And then if I look, that 3 meters is actually where F1 acts. So we don't really have to calculate anything like that. But we should also include where F2 acts relative to one of the ends of the beam. So if I'm measuring from A, we know it's going to be 1/3 times 3, which is just going to be 1 meter. So it's one of those things that, in my opinion, I believe that you guys know how to solve where the force is. You guys don't really have to show any math to do it. You can just label it on the diagram like I did, because you guys are smart. We know that you guys know exactly what you're doing, so stuff like that. Alrighty, so now that we have our free body diagram, it has everything that we need, we can start solving for the unknowns. And the first ones is, let's start with the unknowns that we know how to solve for really quickly, which is F1 and F2. So if I were to go F1, we know it's going to be the area of that rectangle. So the height of it is going to be the 600 newtons per meter, and the length of it is going to be that 3 plus 3, which is 6 meters. So if I toss all that in, I'm going to get 3,600, and the units of force were newtons, so it's going to be 3,600 newtons. We can do the same for F2. It's going to be the area of that triangle. So we know for a triangle, it's always going to be 1/2. And then the height of that triangle, even though it says 900, remember, 600 of that was already accounted for in the rectangle. So the actual height of the triangle is going to be 300, because we're only looking at that relative height. And it only spans the 3 meters, not the whole 6 meters. We throw that in, we're going to get 450 newtons. So 2 unknowns right off the bat, good to go. We can start solving for our unknown equations. So remember, we have 3 equations to work with. We have sum of the forces in x equals 0, sum of the forces in y equals 0, and sum of the moments about any point equals 0. So now we're going to have to ask ourselves, okay, well, if I were to take sum of the forces in y right now, I'd have two unknowns. I have ay and by. So if I did that equation right now, I wouldn't be able to solve for anything. Two unknowns with only one equation, not going to work. So the key to this is always finding the equation that's going to give you an answer right off the bat. So if we usually look, and for beams, this is usually the case, and I say usually, so please remember usually. I don't want a lot of people for doing this and then getting it wrong, say, oh, Clayton told me. No. I'm saying my disclaimer right now. So usually for beams, there's very rarely a lateral load or horizontal load. So if I were to look at this real quick, and I were to go sum of the forces in the x direction is equal to 0, we would have bx and then plus, and if you look at the beam, there's nothing else. So instead of plus, well, there's nothing else, we erase the plus. We know bx must be equal to 0. So that's kind of a nice, quick, easy one. So remember, this is going to be a final answer because it's support. So let's just box it in real quick. So bx is equal to 0. So there's our first one right off the bat. Like I said, for beams, usually the case. However, when you get into more 3D, not 3D structures, but 2D structures with height, let's say a truss, and it has a lateral load, there's a very good chance that bx won't be 0. So now you got to ask, okay, well, we got two equations left, sum of the moment and sum of the forces in y. And we already discussed that for the y, we need ay and by, which we still don't know. So that's probably not one we're going to want to do. So what we're going to want to do is we're going to want to switch to the other one, which is sum of the moments equals 0. But remember, we have to take that moment at a very specific point, And now here's kind of the trick that you guys can do. And it's a nice trick. Always kind of works, always gives you a lot of good answers. I'm just going to make this 0 look a little bit better. So when you're dealing with sum of the moments, and when you want to get rid of as many forces as possible, and you have a pin. So the trick is you have a pin. Always take the sum of the moments about that pin. So remember, we had a pin at B. So if I were to take sum of the moments at B right now, we see that both bx and by actually cancel out. Well, not cancel out, but they don't create a moment because they intercept that pin. So they don't create a moment. So our only unknown in this equation is going to be ay. So if we look at this, sum of the moments about B, we know it's going to be force times distance. So ay, and it's going to have a distance from point B of 6 meters. So the 3 plus 3, so 6. The next thing you want to do, though, is make sure, okay, is this moment going to be a positive one or a negative one? So if I were to hold my pencil at B and push up, we see that it starts rotating clockwise. So we know if this is actually going to be a negative moment. So we're just going to include the negative sign. We can move on. Well, we got F1, so we got 3,600 newtons. So 3,600. And the force, or the perpendicular, the perpendicular distance to B, we already see as 3 meters, so that's nice and easy. Put 3. And then again, is this going to be a positive or a negative moment? So if I hold my pencil at B and press downwards, we see it starts creating that counterclockwise rotation. So we know this one's going to be positive. Now we can do the same thing for the 450. Now the trick is to know, okay, well, this perpendicular distance is going to be that 6 meters, and we have to go a meter back, so -1, it's going to be 5 meters. So that's kind of the only real trick. It's not too hard. And remember, this equation must equal 0. Okay, so that's not too bad. We can easily solve that using algebra. We move ay to the other side, and we divide everything by 6. What we get is ay is equal to 2,175 newtons. And then what I like to do for support reactions, because it'll help you guys later, is I like to just put an arrow on which direction it's actually going. So we got a positive answer, so it means that the direction that we assumed was correct. So if we look at the beam, we assumed it was going upwards. Our answer was positive. Therefore, we know it actually was the correct answer. So I'm just going to put a little up arrow. But if it was negative, we know that that means that it would still be 2,175 newtons. The only difference is it'd be going downwards. So how I would state that is I would write 2,175 newtons. So I'd still keep it positive in my final answer, but I would just move that arrow pointing downwards. So I let the arrow define the sense of it. So finally, we can go sum of the forces. Oops, I'm not going to do it in red, or else that'd be really confusing. We're going to go sum of the forces in y equals 0. So if we look at this beam, we have AY going up, but instead of putting AY, we actually know the value of AY. So it's going to be 2175 newtons, and that was going upwards, so it's positive. And we're going to minus F1 and F2 because they're both going downwards. So minus 3600. So that's F1, and minus 450. That's F2. And we go plus BY because we're also assuming BY is going upwards, and that's equal to 0. So again, we have one equation, one unknown. This equation is even easier to solve. We get BY is equal to 1875 newtons. And again, it's a positive answer, so our assumed direction was correct, and our assumed direction was upwards. So we can just put it like this, and there we go. So, ooh, that box doesn't look too good. Let's try and just make it just a little bit better. So if we look, we have our 3 support reactions, we had our free body diagram, and that's basically the question. So as you guys see, it's not actually a bad question at all. It's actually kind of really easy, but again, this is supposed to be easy, and what you guys will see in the coming weeks is if we're dealing with a truss structure and we're trying to determine the forces inside of the truss, finding these support reactions will maybe be, if this was a final and the questions were 10, finding these support reactions will probably just be 2 marks out of 10. Something small like that, because these are supposed to be easy. So don't try and overcomplicate things. Don't think you're going wrong because it is too easy. Nope. It's supposed to be easy. It's supposed to be kind of the first step in solving much larger problems. So thank you guys all so much for listening. In the next tutorial, we're going to go to the second case, which is when we have a fixed connection. So when we have that moment. So that'll be a good one to talk about. So I know I said this, but thanks again so much for listening, and I'll see you guys in the next video.